We are into chapter 11 now, where we're going to be talking about parametric equations and polar equations. And we're going to be kind of flipping back and forth and talking about kind of a pre-calc or algebra 2 review of what parametric and polar equations are, and then connecting those to our calculus ideas like derivatives and integrals. So starting out in our first section, we're going to be talking about parametrizations, that's parametric equations of plane curves. So only x's and y's, no z's, no three-dimensional equations here, just x and y equations. So what a parametric equation is it gives separate equations for the x and the y position of a point, both in terms of t, which we usually think of as time. So as time passes, how is the particle moving? And so then we can get some really strange curves like the one here, tracing out the path of a particle according to its x and its y positions. So in a parametric equation, you're actually going to have three pieces to the parametric equation. You're going to have the x equals and y equals equations that are both functions of t, which again we usually think of as time. And then you're going to have an interval of t values. Now that might be kind of an unlimited interval from negative infinity to infinity, or it might be limited to, t is greater than or equal to 0, or more limited than that, but we're going to have some range of t values and then an x and a y equation, both in terms of t. So let's look at some examples of how to work with these parametric equations. So for our first example, we've got our x equals equation is going to be t squared. Our y equals equation is going to be t plus 1. And what we want to do is turn this into a y equals equation. So your homework will look something like this. We want to turn it into a y equals equation where y equals a function of x, not just a function of t. So we're not just going to take that t plus 1 and type it in there. It's not asking for just the y part, but it's asking if this were an xy equation, or we call that a Cartesian equation or a rectangular equation. Those are all going to be synonyms. If this were an xy equation, what would need to go in there? So what we're going to do that is we're going to take that x equation and we're going to solve it for t. So I take a square root of both sides, and t is a positive and negative square root of x, then don't forget our plus and minus. Now what we're going to do is a substitution. So like in Algebra 1, when you're learning about systems of equations, which is kind of what we have here, we have two equations that are working together. We can substitute or plug in one piece for another. So since t is equal to positive and negative a square root of x, we're going to pop that into the t spot of the y equation. So that y equation then turns into y equals a positive and negative square root of x plus 1. Okay? All right, let's look at another one. So in our next one, let's say that we have x equals the cosine of t, and y is equal to the sine of t. On this one, we're going to take a little bit of a different strategy. We want to do the same thing where we're going to come up with a y equals equation in terms of x. What does y equal in terms of x? But trying to do that same strategy as the last one, to solve for t in that x equation, we would have to do inverse trig. We'd have to do an inverse cosine to undo the cosine. That's going to get kind of messy then when we go try to plug that in. The other one would be the sine of the inverse cosine of x. That's it's true, but that's kind of ugly. So what we're going to do is use kind of the most popular of all the trig identities, which is that x squared plus y squared is equal to 1. If we have, let's see, let's change that out actually. So again, about trig, that would be a circle, right? X squared plus y squared equals 1. That'd be a circle. So I kind of like, oops, hint, spoiler alert, that was the end of the problem. Okay, so going back to the most popular of those trig identities is that sine squared of whatever our variable is. Maybe we won't use x because we already have x's going on here. Maybe we'll use theta plus cosine squared of theta is equal to 1. Okay, so that's the actual trig identity that I meant to write up there, and then I kind of gave away the end of the problem. So we'll call it foreshadowing instead of a spoiler. So sine squared plus cosine squared is equal to 1. So if we're going to use that, then these equations are singular powers of sine and cosine. So we can do whatever we want in an equation algebraically as long as we do it to both sides. So if I want to, I can square both sides of these equations and change them to cosine squared as long as I change to x squared. And I can change it to sine squared as long as I change it to a y squared. So then, if cosine squared is x squared and sine squared, well, that's y squared equals 1, then we have actually an equation of a circle. So x squared plus y squared equals 1. And actually, as I'm thinking about it, I think on the answer, this one actually, it doesn't have the y equals. It just has like a box and asks you to type in the equation that we could make out of this. So then that equation, usually, I don't know why, but we put the x first. So x squared plus y squared equals 1. I think it'd be fine if you put the y squared first. Same thing. Okay, and so then it ends up graphing a circle with a radius of 1. Okay, so let's generalize this a second. And let's say that in your problem there was some a value. Well, then when you square it, you would also be squaring that a value as well, right? And let's make it the same a value here for simplicity. That also then will keep them the same, so it keeps it a circle. If they were different, then maybe you remember from pre-calc, that would actually kind of stretch the circle in one direction or the other, creating what's called an ellipse. So then when we would go plug this in here, if we had an a squared there and an a squared there, well, it's like half of the equation has been multiplied by an a squared. Well, that means this other half is going to have to be multiplied by that a squared as well. And so what you're going to end up getting then is a circle still, but adjusted for that coefficient. So coefficients in the front of the sine and cosine, totally fine. Won't change the fact that it is still a circle. It'll just change what the radius of that circle is. One other thing that can be changed about it is what we call in a trig equation our b value, which is a multiplier of the t. So if we had a b value in there, that actually is going to have no effect on what the curve is. It's just going to have an effect on how fast the particle is moving around that circle. So as the particle is tracing out the circle, is it going at like the standard speed or period, to use a trig word, of 2 pi, that it's going to take 2 pi to get all the way around, or is it going to speed it up and it's going to get around in just a pi? So it won't change the equation, it'll just change what interval of t we would need to graph out the entire path. And we'll look at how we can graph these in Desmos as well, and so that you can see what effect that t value has. And actually we'll just flip over to Desmos now and look at how to graph these before we go on to our last example. All right, so to graph parametrics in Desmos, I'm going to look at that first example that we did, which was the x is equal to this t squared. And so what you're going to want to do is enter it as like a point, like an x comma y. And so the x part of it is the x is equal to t squared, was that first example. And then comma, the y equation was y is equal to t plus 1. And then here it gives us our interval for t. So you could choose how much you wanted. Now let's say that it was going from negative infinity. I don't think Desmos really likes infinity. If we do all, no, yikes. Okay, so Desmos isn't really like infinity there, so I'm just going to do like negative, 10,000, whatever. Doesn't matter, just big number onto big number. And we can see then what this is going to end up creating is a sideways parabola with a vertex shifted up one spot, which is the equation that we got when we turned it into our x and y equation. So a couple things to do with this. One thing to do is that in parametrics, it not only matters what curve it ends up graphing, but the trace of the particle. In what direction is the particle going? Like, is it going this way? Is it going this way? What direction is that particle going? So what I'm going to do for that is I'm going to make a second copy of this equation, except I'm going to use the letter A, and then I'm going to create a slider for A, and then you can have A go, I would say probably best to go from like, well, maybe we don't want to go that far. The same as what your T is, but I don't want to go all the way out to 10,000. So now as we start small, and so let's pretend like we're starting at negative infinity. We wouldn't see it for a really long time. As that T is coming along, or we've replaced the T with an A, we can soon here see what direction that particle is going. So that particle is going from the low on up to the high. Okay, so creating the second equation and slider, we can see the direction of the curve. And so the direction of the trace is important. Now, one other thing you could do with this is after you think you've turned it into a y equals equation, you could check and make sure that it actually graphs the correct thing. So we thought it was going to be y is equal to, now we thought plus or minus. I don't know if Desmos has a way to do plus or minus. I don't think so. So I'm just going to do a square root of x and then plus 1. Okay, well that did the top of the curve for us. And if we do y equals the negative square root of x and then plus 1, that creates the bottom part. And so it completely covers what the curve was, and we know then we have come up with the correct y and x equation. Okay, so that's how you're going to graph parametrics in Desmos, if you so choose, is to plot it as a point, like an x comma y, with our t there. And then if you want to be able to see direction, create a new copy with A with a slider so that you can slide that A over and see which direction that particle is traveling. You can then also check your y equals equations that way. Okay? All right, one other example. We are going to look at how to write an equation of a line segment. So we're going to write a line segment that starts at the point -1, -3 and ends at the point 4, 1, and our t is going between 0 and 1. Okay, so what we want to do is come up with a parametric set of equations that would graph this line segment. So for that, what we're going to do is we're going to think about x and y separately because that's what parametrics do. So for x, I'm going to make myself 2 points that I'm going to say are t comma x. If t is equal to 0, well, that would be that starting point. Then x was -1. And t comma x, if t is equal to 1, then x is 4, the x from the other point. So x's begin at -1, end at 4, as we travel from t is 0 to t is 1. Now I want to write like a y equals mx plus b equation for that. So I need to know slope. Slope is change in y over change in x. So slope is 5. So x is equal to slope t plus b, which is our starting point. So when t is equal to 0, what is x equal to? negative 1. And we can then check that according to those 2 points. If we plug in t is 0, we should get x is negative 1. And if we plug in t is 1, we should get x is 4. And so that works out. So that's our x equation. And then for y, I'm going to do the same thing and say t comma y points where t is 0, y is negative 3, and where t is 1, y is 1. So the y values of each point according to the t interval. So find slope again. So change in y over the change in t. And that gives me 4 as my slope. So my y equals is y is equal to 4t, and then I need my plus b at t is 0, y is negative 3, and we can double check that. If we plug in 0, we get negative 3. If we plug in 1, we get 1. So it starts and it ends at the right spot. And so those would be the parametric equations that would graph that line segment if t is going from 0 to 1. And again, you could check that on Desmos. You would type it in as the x equation comma the y equation, and then you would just set your t to be from 0 to 1, right? And to make sure that it's starting and stopping at the correct points there. Okay, so let me know what questions you have as you work on this more algebra pre-calc review of what parametric equations are and how to move back and forth between parametrics and Cartesian or XY equations. All right, talk to you guys later.